So this unit is going to introduce us to dynamics, which is looking at forces and why things move the way that they move, whereas Unit 1 was just describing the motion of objects. So a force is a push or a pull on an object, and the variable that we use for force is the capital letter F, and then we typically have a subscript that's going to identify what kind of force that is. So APP is sort of a generic one that's means applied force. But there will be other ones that we'll look at, like F sub T, which means tension, which is a force caused by a string, or F sub G, which is gravitational force. And I'll go through those later, and you'll begin to learn which ones they are. The unit for force is actually kilograms times meters per second squared, and that's also called a Newton. So it's a derived unit that is given a name. A Newton is written with a capital letter N. You can also write this for the unit. It is valid. And it kind of tells us the equation that we have for force. So if kilograms times meters per second squared is the unit, then the equation should be that a force is equal to mass times acceleration, which is Newton's law, and we'll see that here in a second. I'm going to skip over this. We'll talk about pounds in a minute. Pounds is a unit of weight that we use in America, and it is not a physics unit. So Isaac Newton, really, this idea of forces is going to run through the rest of the semester because this is all of classical physics, which is pre the early 1900s. All modern physics is stuff that sort of happened after that, like Einstein sort of stuff. But we spend the all of AP Physics 1 talking about something, and parts of AP Physics 2, if you're taking that, like learning about Newtonian mechanics, which is, all of these like fundamental concepts we're going to cover in this unit are going to be important for everything we do from here on out. So Isaac Newton came up with 3 different laws. We're going to talk about Law 1 and Law 2 here today. So Newton's first law is the law of inertia, which you've probably heard this before. An object stays at rest unless a non-zero force acts on it, or an object stays in motion in a constant straight line specifically, unless a non-zero force acts upon it. So an object at rest stays at rest, or an object in motion stays in motion unless there's a force. All right, so what does it mean if there's no force? That is, or if the net force really is equal to 0. This is a situation called equilibrium. So equilibrium is can be either static or dynamic. Static equilibrium is when all of the forces are balanced out. So it doesn't mean that there's no forces at all. It just means that all the forces to the right equal the forces to the left, and the forces up equal the forces down. If the object's not moving, that the velocity is equal to 0. That's called static equilibrium. Now, that's pretty easy to understand in terms of forces. Dynamic kind of trips people up a little bit because this is when an object is moving, so it's moving with a constant velocity, but all the forces are balanced. Up forces equal down forces and right equal left, and therefore the object is in motion, but it's considered to be in equilibrium, dynamic equilibrium. Right? Notice that both of these cases, you have acceleration is equal to 0. So remember that forces make things accelerate, right? So the idea of the relationship between your force and your acceleration really kind of leads us from the first law to the second law. But before we jump into the second law, we kind of have to define this word inertia. So inertia is really your resistance to your change in motion. If you're at rest, you want to stay at rest. If you're in motion, you want to stay in motion, right? And it really is a measure of your mass, or how much matter that you have in you, right? Now, why do I have a rhino here? Essentially, this just says to us, what would you do if you're being chased by a mad rhinoceros, right? So the idea of a rhinoceros has a huge amount of mass. So if it's running, it's going to take a lot of force for it to change its motion because it resists change in motion. That's what inertia is. Whereas if we're running away from it, you have a lot less mass than a rhino, so it takes less force to accelerate the same amount, right? So if you're going to try and get away from a mad rhinoceros, you just got to zigzag around or run in circles, kind of like bullfighting, right? So that brings us to the mathematical explanation of force, which is Newton's second law. So if there is an unbalanced force acting on something, or a net force, then the object will accelerate. And the equation here, and remember this goes back to the unit, you have F net is equal to, or another way of saying F net is saying the sum of all forces, is equal to the mass, and that's the mass of anything that's moving, so we rarely say the mass of the system, times acceleration, so kilograms times meters per second squared. So really your acceleration is a ratio of the force, or the push to pull, to your inertia, or your mass, like your resistance to the push to pull. So the ratio of force to mass gives you like your net acceleration of the system. Right, so when I say net acceleration, it really does mean sum of all forces. So forces are vectors, and just like in Unit 2, when we started separating things into their x and y components, that's going to be very important for this unit as well, where we're going to be looking at things moving either horizontally in the x direction or vertically in the y direction, and looking at, right and left forces versus up and down forces. All right, so all forces are really exerted when something is touching something else. However, there are exceptions to that rule, and one of them is weight. The other is electromagnetism, which we'll talk about later. These are field forces. These are forces that are exerted without a point of contact. So if I throw a ball up in the air, there is a force due to gravity that acts on it that makes it fall down towards the ground, even though the earth isn't technically touching the ball. So the force due to gravity is what weight is, and it always is there and always points down towards the center of the earth. So we use F for force and the subscript G to say that this is a gravitational force. And remember that force is mass times acceleration, and this is a specific example of mass times acceleration due to gravity on, whatever planet you're on. So we've been talking about gravity. It's been acceleration due to gravity. So this little g is actually 10. And then you have your mass, so like say you are 15 kilograms, that means that you would have a weight of 150 newtons. And you will hear me say over and over and over, what is Fg? Fg is mg. Where you see Fg, you can put mg. When I say Fg, you say mg. So that will be ingrained in your brain. All right, so really mass versus weight. So remember that mass is how much matter you have. That does not change no matter where you are. But your weight can change, and you can be weightless. So if you go to the moon and you're a 75 kilogram person, you are still going to have a mass of 75 kilograms when you get to the moon, right? You haven't lost any matter, right? But your weight will change because the acceleration due to gravity on the moon is different than it is on the Earth. So if you're a 75 kilogram person, on the Earth you're going to weigh 750 newtons, 75 times 10, which is roughly 170 pounds, just to sort of get you, understanding what these two mean. 122 newtons is what you would weigh when you went to the moon, because the acceleration due to gravity on the moon is a lot smaller. It's actually like 1.7. All right. I am going to talk a little bit about another kind of force here called a normal force and a free body diagram, and then I'm going to give you a step-by-step process to walk through any Newton's law problem that we do forever, right? So if you have a book and it's resting on a table, right, so here's your book, let's say it's 2 kilograms, and it's sitting on a table, we draw something called free body diagrams that actually show the forces that are acting on the object in question. So you're going to have the force due to gravity always if we're on Earth or any planet, right? And that's going to point straight down towards the center of the Earth, right? Now, the book is not like accelerating down towards the center of the Earth, like smashing into the ground, right? So there must be some opposing force, and that force is touching, right? It's caused by the table. Remember, point of contact is where we're going to see all of the other forces. If you can say something is touching another object, it's exerting a force on it. So the force that acts upwards is called actually the normal force. And the word normal comes because it is normal to the surface. It is perpendicular to the surface that the object is resting on. Normal force can also be thought of as how hard something is pushing down onto a surface, or it can be what a scale would read. Like if you're standing on a bathroom scale, if you stood really still, you would make your weight equal to your normal force, and your normal force then would, tell you how much you weighed. But if you jump around on it, or you pull up on something, or you push down on a scale, you can make it read something different. So remember that scales read normal force. So right now, this object is in equilibrium, right? So it is not moving, it is in static equilibrium. So all the upward forces equal all the downward forces. So I could calculate the normal force because Fg would be equal to Fn, and I know Fg is mg, so the normal force would be 20 newtons, right? So let me go, now I'm going to jump to the Elmo, and I'm going to kind of walk you through how to do any kind of Newton laws problem, right? So you really want to start with number one, doing a free body diagram, right? So free body diagrams are specific rules that are designed by College Board. You draw a dot or a box to represent the object. Usually this is provided for you. If it's like free response style question, they'll give you a dot or a box. And then you draw only the forces, not their components, on the object. The arrows have to point away from the object and have to be labeled with only force subscripts, right? So let's say that there is some force applied in this direction and there's some pull back in this direction. We'll call this force pull back, right? And then it's on a table, so there's gravity and there's normal force. So this is a free body diagram that shows an object and the forces, right? They are arrows, they point away from the object, we've got all the forces here, right? Now, let's say this, just for this case, let's say that this thing is accelerating to the right, okay? The second step for any Newton's law problem, after you draw your good free body diagram that labels all the forces and all the things that are touching the object, is to ask yourself, is it accelerating? So in the example of the book, right, the book was just at rest on the table, right? So the answer to that question was no, it wasn't accelerating. Remember, those two instances are static or dynamic equilibrium. So where velocity is 0 or velocity is constant. If that is the case, then we write equilibrium expressions to solve any type of problem, where essentially all of expressions, that just means all up forces equal all down forces, or all right forces equal all left forces. Again, remember, we're going to be dealing with these like vectors and separating them into their components. If the answer to the question is yes, it is accelerating, then in order to solve this problem, we're going to write a sum of all forces equation where F net is equal to the mass of the system times acceleration. So what is F net? Well, we look and we say, okay, this object right here is accelerating horizontally. So the acceleration happens in this direction. So my force equation is going to be in the horizontal direction. So I have a force applied to the right and I have a force pulled to the left. Right? That means that because the arrows point in opposite directions, we're going to subtract. So my net would be that F applied minus F pull, whatever those are, must be equal to mass times the acceleration. Right? If I had multiple forces acting in the same direction, let's say I'm applying a force and doing a pull over here, then the forces would add together. For this reason, from now on, we're going to let the direction of the arrows indicate whether or not we're adding or subtracting, rather than making gravity -10. Right? And that will become obvious as we move forward. So if you can follow this system, you can really solve any Newton's law problem, and you'll have a lot of practice on the first worksheets, and we'll continue to do this all the way through the next unit where we talk about circular forces.